Alright, so this is a screen recording of the solution of the final exam of CISP 440. So what I'll do is I'm going to answer the questions, one by one, the same way that you would do it in class. Let me show you the visor window. Okay, so this is the first question. The first question is really just asking you to um, um, give me a trace of the algorithm when it runs. And it's kind of difficult to do it on a small screen because that's all I have for recording. So what I'll do is I'm gonna cheat a little bit. I have a browser in the back end, okay, which is this one here. Oh, there we go. So I'm gonna use this one to look at the algorithm and the graph at the bottom, which you cannot see on the screen because and if I scroll it up you can see it here, but once I scroll it down you cannot see it. But that's what I'll be looking at in order to work on the trace. There's also the heuristic function that is kind of really important to work on too. So that's also one thing that I'll put in first, is to put in the heuristics. And also the cost of the distances. So let's do that first, and I'm gonna put this here where I can see it, and then you'll be looking at this. Okay. All right. Let's see. Huh. All right. So the first thing we need to do is to associate the distances to the edges. So we'll just go ahead and put those here. The edge AB has a cost of 2. The edge AJ has a cost of 8 distance. BK has a distance of 3. JM has a distance of 4. KJ has a distance of 2. MB has a distance of 1. KP has a distance of 8. And MP has a distance of 1. Alright, so there we go. And then the next thing we need to do is to come up with the heuristics. According to the question, the heuristic between any vertex V and P is the actual distance of the shortest path from vertex V to vertex P. Okay, so let's work with VKP first. So that's going to be 8 because that's the... Oh, okay, that's not the case. Okay, because from K, which is here, to P, the lowest cost path is actually to go to J, and then M, and then back to P. So that's a 2 plus 4, which is 6, plus 1, which is 7. There we go. And then M to P is either 1 or 1 plus 3 plus 8, which is 12. So obviously the 1 is the smaller one. Okay, and then we work with BP. From B to P, we have 3 plus 8, which is 11. That's one path. And then the other one is 3 plus 1 plus 4 plus 1. So 3 plus 2 plus 4 plus 1. So that's 1 less than the other path. So it's 3 plus 7, which is 10. Okay. B of J, H of JP is 5. And then H of AP, which is either going to B or J. The one from B is the shorter. So we have, the one from J is closer. But because of the edge, 8 here, 8 plus 5 is 13, and then 2 plus 10 is 12, so 12 is the shorter path. There we go. So now we have the heuristics for each thing, and then we also have the diagram here. And then the problem is when I refer to the algorithm and trace it, I have to look at this picture all the time. So let me see what I can do. I'm going to do this. So what I'm doing right now is I am taking a screenshot of just that portion of the screen. Okay, so this is me taking a screenshot of this portion of the screen, so I can refer to that all the time. And then we'll put it, let's see, open with, I need a viewer to open it. There we go. Okay, so let me show you what I got here. So I got this, which is just a screenshot of what I talked about a little bit earlier, and I'm gonna put it right outside of where you can see it, because only I need to see it as I follow the algorithm. So this is the algorithm, and I'm gonna scroll it out of your view as well, so that only I can see it. And then we go back to the trace window, which is all the way to the end on the last page. Alright, so there we go, and now we can start to work on this. Alright, so the initialization is that G of S, the start vertex, has a 0. Okay, so remember, in class we talked about the different ways to work on this, and one way to do it is to have a G value for every single vertex. So we have the G value of A. I'm looking at the graph here. B, J, K, M, and P. And then same with all the other one. We got A, B, J, K, M, P, A, B, J, K, M, P. Okay, so that makes the tracking a little bit easier. For the previous, it is all undefined to begin with. So they're all undefined. And then for the G value, only A has a non-infinity beginning value. And then for the F value, A is the one that has the heuristic, but in this case, the heuristic of A to P is 12. So that's why F of A is 12, and then for everybody else, they're all infinity. Okay, so this initialization by itself is worth obviously some points, because if you don't get it initialized correctly, things are not going to work. All right, so as we finish the last part of the initialization, we put the starting vertex into O. The starting vertex is already given to you as A, so the O is now a set with just the element A. And that's it. That's the full initialization, and I'm going to back this up to the previous row. Okay, so we'll put it into this row here to indicate that the open set only has one single element of A. Okay, so let's see. I'm just checking to make sure that the volume is still good, because it has been known to cut out in the previous recording. Okay, so now we go into the algorithm, where it says, as long as O is not empty and every element in O has its F value less than or equal to the G of P, which is our destination. Well, since G of P is infinity, that requirement is satisfied. So the next thing we do is we pick out the element in O that has the smallest f value. Since we only got one element, we don't really have that much of a choice. So we pick A, and A has two neighbors. We have to explore both neighbors, but before we do that, we have to update O so that now it is an empty set because A is removed. And then we go to line 13 of the algorithm. We basically say, okay, let's consider all neighbors of vertex A. We can explore B first. Okay. So as we explore B, we are going to evaluate what is g of A plus the distance of AB. So if I just kind of pop this into your view quickly, there you go. So you can see that g of A is 0 plus the edge of 2 distance. So t is 2. So we'll update t here as 2. And then 2 is less than the g value of b, which is infinity at this point. So we will go into here. The first thing we do is we update the g value of b. So it goes from infinity to 2. And then the f value of b is going to be updated as well. So it's going to be 2 plus the heuristics from b to p, which is 10. So 2 plus 10 is 12. So we update this guy to 12. Everything else is maintained. The previous of b is now updated to a. And then we also have to remember to put b into the set of O. And we look at the next neighbor. We can put all of these items into the previous row too. So let me just kind of do this. So this way it is the trace is a little bit more compact. And I'm going to use an eraser because I cannot just undo this. There we go. All right, so B is one neighbor, the other neighbor is J. So when J is the neighbor, 0 plus 8 is 8, so T is 8. And when we compare 8 to G of J, which is infinity, 8 is less than infinity. So we update G of J to 8. And then we also have to update the H value of J. So that's going to be 8 plus 5, which is 13. So the F value of J is now 13. And then the previous of J is now updated to A. Okay. And then we have to remember to add J to the set. There we go. So that concludes the for each loop. We get back out onto the while loop, and obviously O is not empty, and because G of P is still infinity and all the F values of B and J are less than infinity, so we get to continue. Okay, so when we pick the next variable C, we have to pick the vertex that has the least F value. And the one that has the least F value is B, because F of B is 12. So we pick B here, and then we remove B from the set O. So J is now the only thing remaining. Now we have to explore all the outgoing edges of vertex B. So according to this diagram here, B has only one outgoing vertex to K. Okay, so we explore that K here. BK is the edge that we are looking into. We have to evaluate T. T is the G value of B, which is 2, plus the edge distance of the edge, which is 3. 2 plus 3 is 5. So we put a 5 here. And now we ask, is 5 less than G of K at this point? So G of K is infinity, and 5 is definitely less than infinity. So we're going to update the G value of K, and now it is 5. We are also going to update the F value. The f value, or the k value, excuse me, the h value of k is 7. 5 plus 7 is 12. So now the f value of k is also updated to 12. Okay. We have to update the previous of k so that it is b. There we go. And we have to add k to the set O because its value just got updated. So now the for each loop is done because b only has one single outgoing edge. Then we go back to the while loop, which looks at the set O. It is non-empty. Okay. G of p is still infinity, and all the f values of j and also of k are less than infinity, so we get to continue. And the first thing we do is to select the one element in O that has the lowest f value. Of the two elements left here, which is j and k, f of j is 13, f of k is 12, so we're going to pick out k because that has the smaller f value. So k is what we are going to pick out first, and then we have to look at all the outgoing neighbors of k. K has two outgoing neighbors. It goes to j and it also goes to p. So it doesn't matter. Okay, let's pick p first. So we're looking at p, which is also our destination vertex. We evaluate g of k. G of k right now is 5. Excuse me. Excuse me. Okay. G of k is 5. And then we add that, the distance of the edge kp to 5. 5 plus 8 is 13. So we put 13 here. So is 13 less than g? Oh, that looks like a b. Let me fix that. There we go. So now the question is 13 less than g of p at this point? G of p is infinity. So 13 is definitely less than that. So we update it here. And then we also update f of p. F of p is also going to be 13 because h of pp, which is the heuristic of going from vertex p to vertex p, is 0. Okay, so that's 13. And then the previous is updated to k for now. Okay. And then we have to add p to the list. So j, k, and p. There we go. And then we're done with this iteration of the for each loop. There's another iteration of the for each loop because k also goes to j. So now we put j here. And then we ask what is t this time. So t this time is 7 because g of k is 5, and then the edge from k to j is only 2. 5 plus 2 is 7, so that's 7. So now the question is 7 less than the current g value of j? The current g value of j is 8. 7 is less than 8, so that means we have to update it. Okay, so now we update the g value of j to be 7, which also means we have to update everything else. We also have to update the f value of j. According to the h value of j, it is only 5. So 5 plus 7 is only 12. So we have to update the h value of j to 12. We also update the previous of j so that instead of going from a, it is now coming from k. There we go. And then we're going to put j into the set. But j is already in the set. Okay, I forgot one thing here. Alright, let's fix this. Because k is not supposed to be here anymore. Because when I pick out k as c, I should have erased it. So there's another update here. K is removed from the set. So now we are adding J back to the set. J is already there, so there's actually no change. But we still have to kind of indicate that there's a quote-unquote update to the set O. So now we are done with this. We're done with the for each loop. We go back to the while loop. The while loop this time is a little bit tricky because G of P is 13, and then we have to look at the F value of J and P. The F value of J is 12, which is less than 13, so we cannot get out yet. Because as long as there's at least one. Okay. Okay. It says for all. It really should be a there exists in the while loop, but it's okay. I'm just going to follow the algorithm at this point. Every single F value is still less than or equal to the G value of the destination, so we're still good. Okay, so now we get on to line 11, which says select C in O such that this particular C has the smallest F value. Of these two, J and P, J has the smaller one, so we pick out J here, so the P is the only thing remaining in the set. And then we look at J and we ask who are the outgoing neighbors of J. There's only one, which is M. And then we look at G of J. G of J is 7 plus the cost of that edge JM, which is 4. 7 plus 4 is 11, so T is now 11. And then we ask, is 11 less than the G value of M? The G value of M is still infinity, so it is less than. So we get into the conditional statement. We update G of M to be 11. We update the F value of M so that it is 11 plus the heuristic of M to P, which is 1. 11 plus 1 is 12. So we put a 12 here. And then we also have to update the previous of M. So it is now J. So there we go. And then we add M to the set. So the set O now has M and P as its elements. And this concludes the for each loop because there's only one outgoing edge from J. And this is also going back to the beginning of the while loop. So in the while loop, we have two elements left in the set. And the F values of both of these are less than or equal to the G value of P, which is 13. So we still have another iteration to go at least. Of the two elements in O right now, the F value of M is 12, the F value of P is 13. So we're going to pick M. Okay. And then we look at all the outgoing edges of M. It has two outgoing edges. One is back to B, the other one is going to P. Well, just for Kaka, we'll look at P, the one going to B. So now we have to compute the G value of M. G value of M is 11, plus the cost of the edge to B, which is 1. 11 plus 1 is 12. So the question now is 12 less than the G value of B at this point. The G value of B at this point is 2. 12 is not less than 2. So there's no update. There's no update for this entire row because the condition is false for the conditional statement. Now we look at the other outgoing edge of M. The other outgoing edge of M, I'm just realizing that just in time that let's move this one to over here. Well, we can put it maybe on top. Yeah, I think that's fine. So we'll put it on top here. So the other outgoing edge is from M to P. Okay, so P is the other outgoing neighbor of M. And then we ask the question, what is the t? So this is g of m. So g of m is 11 plus the edge from m to p, which has a distance of 1. 11 plus 1 is 12, so we put a 12 here. Is 12 less than the g value of p at this point? The g value of p is 13. 12 is in fact less than 13, so we update g of p to be 12. And then we look at all of the, we update all of the other columns too. The f value is going to be 12 also, because the heuristic from going from p to p is only 0. So 12 plus 0 is only 12. The previous p is updated from k to m in this case. And then we also have to add, oh, I forgot to update this. Since we picked out m, we only have p left in the set. And in this particular step, we are adding p to the set O. But since p is already in the set, it doesn't seem that it has changed. You can say no change or NC if that is the case. And then we are done with the second iteration of the for each loop. And then we go back to the while loop. So in the while loop, we go back to the beginning. We only have one element left in P, in O. And because I said as long as all the f values are less than or equal to the g values, you can see that the f value is 12. The g value is also 12 for the only element left. So we're going to have to pick it out too. So we picked out P. And there's nothing to do because P has no outgoing edges. So we are basically done at this point. We go back to the while loop. The while loop says, okay, O is empty. So that's one of the conditions to get out of the loop. So now we go to the for each loop to figure out what is the edges. Okay, so I can't go too far. Okay, so what I'll do is I'm going to put it on the top here. So E prime is, we evaluate every single vertex if the previous of a vertex is not undefined, then we add that edge to the set. Okay, so we look at each one. A is undefined, or the previous of A is undefined, so there's nothing to do here. The previous of B is A, so the edge AB is going to be added here. The previous of J is K, so KJ is going to be here. The previous of K is B, so BK is going to be here. Oh, you cannot see it because I'm writing over the area that the graph is over, it's on top of. So BK, we look at M. The previous of M is J, so JM. And then the previous of P is M, so we got MP. Okay. Let's see if that makes sense. Okay. So I'm going to look back here and use my mouse pointer instead of my stylus. So the shortest path is A, B, K, J, M, P. I think that's the shortest path because that particular path has a length of 2 plus 3, which is 5, 5 plus 2 is 7, 7 plus 4 is 11, 11 plus 1 is 12. I think that is the shortest path. So let's see if that all the edges are in the set E prime. AB is here, BK is here, KJ is here, JM is here, and then MP is here. So we got all the correct edges in E prime. It's just a double check to make sure that things are done correctly. So that answers the first question. And if I just remove this thing here, that will show you the answer of the first question. So that's the answer for the first question. Some of the sequences can be different. In other words, every time we look at outgoing edges, like these two rows can be swapped. these two rows can be swapped, and these two rows can be swapped. Um, but swapping those rows really should not affect the overall values of the algorithm. I'll be looking at J getting updated twice. So you can see the previous of J, along with G, and also the value of J is updated twice. Okay. We also see that the value of P is also updated twice, right here and right here, right here. So I'll be checking for all of those things. There are slight variations of this algorithm, as I said, but other than that, the sequence of updating really should not be too different. Okay, next. Okay, so let's move on to the next question. Question number 2. Okay, so question number 2 is asking the construct called prev in A star algorithm can be seen as a function, blah, 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 blah. And the first question is really just to say, okay, what makes a function a function? Okay. There are two requirements. So the first requirement is every element in the domain maps to, well, actually, I can combine the two. One and only one element in the codomain. Okay, so that's basically the bottom line. And obviously in this case, this is our domain and this is our codomain. Okay, next, describe why prev is a function before the first iteration of the while loop after initialization. Well, after initialization, everything is initialized to undefined. So that means every single element in the domain, which are all the vertices, are mapped to one element in the codomain, which is undefined in this case. So you basically just have to say that in words. The other way you can say that is really just in describing in English, or you can also describe it in a mathematical sense. You can basically state your observation, like, for all V in V, prev okay, let me back up a little bit here. I'm just trying to think of how we state this. V undefined is an element of prev. And undefined is an element of the codomain. Okay, or you can make it even more clear, which is the union between uppercase V and the singleton set of undefined. Okay, and that should be enough. Okay, so the last one is describe why previous remains as a function despite the update of the set on line 18. So we're focusing on just one single line here. So it might be helpful to display that line. So I'm gonna scroll to that line in the algorithm, and that line is right here. So every single time we update the previous, we're updating what n is mapping to C. But what is C? C is okay. So all right. So let me switch back to the tablet. Okay. So on line 18, each update changes. It updates. Okay, I'm just looking at the algorithm again to look at the term. Okay, so it updates n some element e to nc. Okay, so but we know that c is a vertex in V, and as a result, n is still mapping to an element of the codomain. Okay, and that's it. That's the only thing we need to mention. We cannot have two. We cannot have the same element updated to map to two different things because it's an overwrite. So that part does not need to be mentioned. All right. So that's question number 2. Moving on to question number 3. Says the A-star algorithm guarantees to find the shortest path, but only if h does not overestimate the length of the shortest path from one vertex to the destination vertex. And the idea is to mess it up by changing a single h value so that it causes the algorithm not to find the shortest path. In the following space, indicate which h blah blah p value you propose to change is new value and the path that A star will find as the shortest path as a result. Explain why the algorithm is tricked. Make references to line numbers of the algorithm to be specific. No need to trace the algorithm. Your answer has to be in the form of change the heuristic of something to some new value so that the algorithm chooses a different path instead of the actual shortest path. This happens because of which line of the algorithm makes an incorrect decision to branch to whatever part of the algorithm instead of the path that it's supposed to go to. Okay, so let's go ahead and look at the diagram again and also the heuristics and see how we can mess it up. Alright, so according to this diagram, the shortest path is A, B, K, J, M, P. We are only allowed to change one single heuristic value to trick the algorithm to go to the wrong place. Okay, so the question now is, which one are we going to change? And we can change it to some really, really large value, but you can only change one of them. So we have to think about somewhere along this shortest path. Okay, we have to make it go for a wrong alternative. Now it can go from the beginning, okay, from the get-go, it goes to the wrong path. Okay, that's one way to do it. So we go for 8, 4, 1 as the shortest path. So how do we convince the algorithm to go for the wrong path here and not go for the correct path here? And the trick to do this is to make h of b, p much higher than it needs to be. Because h of pb is 10, so we want to make this super expensive so that from the get-go, the f value of b is going to be so high that we are not going to consider it. And since I did not put a cap on how big you can make that h value, you can make it 100. You can make it so much more than the actual length of the shortest path that it will never be picked. Infinity is not one of the options. Okay, so you can only use an actual value because infinity is not an actual value. Okay, so given that, we can now follow the format of the algorithm. So we'll say change h of pb to 100. Okay, so that satisfies this part of the requirement, so that the algorithm chooses the path A, J, M, P, A, J, M, P instead of A, B, K, J, M, P as shortest path. Okay, now we explain it. This happens because, okay, so now we have to be careful. So we have to refer back to the algorithm and then say, okay, how is that going to trick the algorithm? So we refer back to the algorithm, and the thing that it does is it tricks line 11. Okay, because when we compute the f value of okay, when we compute the f value of b, it's going to be much higher than it needs to be. Okay, so let me go back to the, I'm gonna put this one out of the view, switch back to this window here. Okay, put this back here, and we can stash it over here. There we go. Okay, so this happens because f of b is 2 plus 100, which is 102, on, okay, now we refer back to the line numbers. So on line 11, the algorithm does not choose b as variable c. Now, that may seem to be enough, but that's actually not the case, because the algorithm has two conditions to stay in the loop. The first condition is as long as big O, or the open set, is non-empty, which means we may still stay in the loop, and as long as vertex B is still in the set O, there's still a chance of exploring that, because once we explore B, it's going to update the H value of B. Well, it's not going to update the H value of B, but everything after B is still going to have the right H value. So we'll still be able to find the shortest path. So the key is the second part here. The second part is on line 10. This requirement will not be satisfied anymore, because not every vertex of O is going to have a f value that is actually less than the g value. Okay, so we have to add that part into the answer. Okay, so we have here on line 11, the algorithm does not choose B as C, and then when g of p is updated to 13, the while loop exits, because f of b is going to be greater than g of p, which makes the second condition not satisfied. Okay, now make it clear here. Making the right hand side of the while condition false. And that it really is the crux of the whole thing. is we want to stay in the while loop, but only as long as all the f values are less than or equal to the g value of the destination, which basically says, okay, there's still hope that a shorter path exists. But because the f value of b is going to exceed the g value of p, that will fail the for all condition, and as a result we are done, because we are basically saying there's no hope left when b is the only element left in the whole set of O, and we are not going to expand it because it doesn't look promising to us. So since we are not expanding it, we will never find the actual shortest path, because the actual shortest path involves bk, and if we're not expanding b, then it's not going to find the shortest path. So that's kind of the gist of the answer of question 3 of 5. Okay. Now we move on to question number 4. Question number 3. Now we move on to question number 4. Assume the heuristic function h does not overestimate the length of the shortest path. Furthermore, assume there's at least one path between the start vertex and the destination. I propose the following theorem. Right before line 11 of the A star algorithm executes, at least one element of the set O is on the shortest path from S to X. And we want to prove it by induction. Unlike the usual proof by induction, this one requires a slightly different view. Count the iterations 0, 1, 2, and so on. In other words, the induction variable is which iteration we're dealing with, and I is a natural number. The base case is for iteration 0. The induction step should work the same way as a regular proof by induction, except your argument is not based on algebra, but reasoning of steps of an algorithm and what is given as the input of the algorithm. Okay. So, since we're proving by induction, we are going to restate the theorem. Okay. So the theorem is to say for all I as a natural number, the theorem is there exists at least one element, we'll call x in O, such that x is on the shortest path, and this condition applies to line 11 as precondition of line 11. Okay. So now we state a base case. Base case. And that is when I equals to 0. No, so when I is equal to 0, big O only has one element because it's initialized to only have the starting point of the entire set of vertices. Has the start vertex. The start vertex, which has a name S, is on the shortest path. Okay. So the base case is pretty easy to prove because the start vertex is on the shortest path, and that's for iteration 0. So now we have an induction step. So assume, the theorem is true for I equals k, iteration k. Okay, so now we have to look at iteration k plus 1. So switch back to the algorithm. Alright, So when we switch back to the algorithm, we are looking at line 11 again, and we already know that in the previous iteration that is true. So now we have to look at what an iteration can possibly do to make the next iteration also satisfy this requirement. So there are two branches here. Okay, so we have sub case 1. So sub case 1 is in iteration k. C is the vertex on the shortest path. It's the only. And we picked it, right? Okay. So potentially, because we remove C from the set O, we can potentially, make it not true anymore. Okay, so in this case, in iteration K, C is the only vertex on the shortest path in big O. So now we have to look at the rest of it and go like, okay, how do we make sure that we are adding back at least one element that is on the shortest path? Okay. So the key is at least one neighbor n of C is also on the shortest path, or on a shortest path. Okay. So that argument is easy to state because C itself is on the shortest path. So one of its outgoing neighbors has to be on the shortest path as well. All right. So if that is the case, then we have to look at the condition in the loop here. The first one is look at T, which is a G of C plus D of Cn. Okay. So this means T is the length of the shortest path from the start vertex S to N. So that means the condition of line 15 has to be true. Condition on line 15 has to be true. And if that is the case, and that adds n to set O, and that finishes subcase 1, because now n being on the shortest path is now added back to O, and so the condition, the theorem is true. So we have a subcase 2, which is easier. Subcase 2 is in iteration K. Oh, we can conclude this one. So that in iteration K plus 1, n is in O, and the theorem is still true. Okay. So subcase 2 is in iteration K. C is not on the shortest path. Okay. All right. So that's actually easy, because if C is not on the shortest path, this means the theorem continues to be true for iteration k plus 1, and this is because the elements or the vertices, penmanship, vertices that are on the shortest, penmanship is awful, shortest path is still in O. Okay, that's it. That's the entire proof. But it is important to take into the case 1 and sub-case 1 and sub-case 2, because occasionally, depending on whether the heuristic is trying to trick us or not, we can potentially pick a vertex out of O that is not on the shortest path. So we have to separate that into two cases where, okay, if we pick an element that is on the shortest path, then it's a little bit more complex, because we have to now make sure that one of its neighbors, which is also on the shortest path, is going to be put back onto this set. But the other one is, okay, what if we got tricked and we pick something that is not on the shortest path from O? Well, that's the easy one, because that means we still have at least one element in big O that is still on the shortest path. So that's the question number 4. Now moving on to the last question, which is 5. It says, assume the heuristic function h does not overestimate the length of the shortest path between two vertices, and furthermore, assume at least two shortest paths of equal distance or equal length between the start vertex and the destination vertex x. There are two, at least two. I propose the following theorem. After the completion of the A-star algorithm, the solution graph only contains one shortest path. Use proof by contradiction in this case, and it is important to refer to the line numbers of the algorithm. So this one is actually kind of easy to deal with, because you're looking at the algorithm, but this is the question. So so the key is how we construct E prime, and also how we keep track of the previous. So so referring back to the algorithm, the key to this answer is on line 18, because on line 18, the way we update the previous is every vertex can only have one single previous vertex. Okay, so we go back here. So we say on line, okay, since we're using proof by contradiction, let's do it that way. Okay, so the theorem is there is only one shortest path in G prime equals to V E prime. Okay. The negation of the theorem is there are at least two shortest paths in G prime equals to V E prime. Okay, so if there are two shortest paths, that means some vertex needs to have two outgoing edges. Okay, this means at least one vertex, let's call it vertex W, has two outgoing edges, because there is only one start and one destination vertex. So I don't need you to prove that, because there's only one start vertex and there's only one destination vertex, and we have two paths represented, then at least one vertex needs to have two outgoing edges. So I'm not going to require you to prove that. You can just kind of mention this, and we'll consider it, proven. Okay, so the key is at least one vertex has two outgoing vertices, outgoing edges. Okay. But more than that, this also implies that at least one vertex has two incoming edges. Okay, once again, you don't have to prove it, but it's because there's only one start vertex and there's only one destination vertex. And if there are more than two paths to go from the start vertex to the destination vertex, then some vertex needs to have multiple outgoing vertex edges, and at least one vertex is going to have multiple incoming edges. This means, okay, so we're going to say, we'll give this one a name. Okay, so W is already used. Let's WX. X is the destination. Y. Okay, let's call it Z. Okay, so this means the edges. There are at least two edges. We can call it Y1Z and Y2Z are in E prime. Okay. Okay, at least two edges, y1, which is one vertex, and z, which is our vertex that has multiple incoming edges, and then y2, which is the other incoming neighbor of z. They're both in E prime. But we also know that how E prime is constructed in the algorithm. So according to the algorithm in E prime, on line 22, okay, so on line 22, an edge is only added if a vertex has a previous entry. So this means the previous of z equals to y1 and the previous of z equals to y2. But this contradicts that prev is a function. See question, I think number 3. Okay, let me check. Nope, that's question number 2. Okay, so I stand corrected. See question, oops, 2, and that's end of proof. All right, so that's the solution of the final exam, and I'm gonna stop the recorder now. If you got any questions, go ahead and send me an email. I'm gonna start grading the final exam sometime today.